Hello, my name is Nathaniel Librand, and in this presentation, me and Max Vogel will be going over our implementation of encrypted malware detection in a Palo Alto next generation firewall. In our presentation, we'll be going over a brief abstract, as well as the project description and background information. We'll test the system and show our experimentation and results. This project's objective is to address the vulnerabilities posed by the constantly growing threat of encrypted traffic transmission. More specifically, malware entering networks undetected through secure TLS channels. TLS sessions which travel directly between the client and server can allow malicious content to enter a secured network undetected due to inadequate decryption policy. Traditional firewalls are limited in their capabilities of inspecting encrypted packets, since the only unencrypted portion of data in TLS packets is the packet header. The rest of the malicious body of the packet could go undetected, potentially allowing the transmission of malware. Next-generation firewalls are capable of decrypting the traffic, inspecting it, and choosing to either block the threat or re-encrypt the packet and forward it to the client. This project aims to test the effectiveness of next-generation firewall decryption policies at detecting and preventing malware from infiltrating the network through secured TLS channels. Palo Alto next-generation firewalls can split the traditional client-server TLS session into two separate sessions for before the traffic inspection and after the traffic inspection. The initial session is between the client, such as a browser, and the next-generation firewall. The following session is between the next-generation firewall and the server. The inbound HTTPS traffic is decrypted and inspected accordingly, with malicious content being blocked and logged, while safe traffic is forwarded to the client. Decryption policy rules, along with a self-signed certificate, are configured to facilitate the next-generation firewall to act as an SSL forward proxy. The outcome of this project is to highlight the Trojan horse qualities of HTTPS traffic, which allow malware to enter networks undetected, and how the next generation firewalls can mitigate these threats from going ignored. So here you can see that I have the malware file open, and if we go in and click download, you can see that it lets us do this without any sort of issues or trying to stop us. And this is because it is in an encrypted traffic, so the firewall can't actually decrypt it and inspect it at this point. Let's start by going over some background on the protocols we'll be discussing. HTTPS is a transport layer protocol which establishes end-to-end encrypted communication between a client and a web server. SSL is a security protocol which encrypts, decrypts, and inspects TLS traffic across secured channels. SSL certificates are identifiers issued by trusted certificate authorities to web servers for the purposes of authentication. A Trojan horse is a type of malware which can enter a secure network by concealing itself in legitimate traffic. A firewall is a network security tool which inspects and reacts to traffic based on configured security rules. A next-generation firewall provides improved security tools with enhanced packet inspection, intrusion prevention, policy management, and more. Lastly, an SSL forward proxy is essentially a device which acts as the man in the middle, responsible for the inspection and forwarding of encrypted traffic and client-to-server connections. Let's take a quick look at the system we'll be working with. The lab infrastructure included a DMZ, or Demilitarized Zone Server, a client device, a Palo Alto Next Generation Firewall, and a router which connects to the external network. The internal network, designated by the yellow, represents the trusted network, where client devices are located. The demilitarized zone is a layer of separation for the servers that may need to be accessed from inside and outside the network. The firewall controls traffic between these zones, ensuring security policies are enforced across the network. The external network, designated by the gray cloud, represents the untrusted network. This is where the router that connects to the internet is located.
The decrypt user traffic policy rule is configured to decrypt any URL category/service traffic between the connections from the user's net zone to the extranet and internet zones. Following the decryption and inspection of traffic, it is then re-encrypted and forwarded via a new TLS session. The no decryption policy rule is created to exempt the traffic of the URL categories that may contain PII, such as government, shopping, and financial services. The no decryption rule is prioritized first to filter out excluded traffic containing PII prior to inspection. The new TLS session created after the decryption policies will require the next generation firewall to issue a new SSL certificate. The self-signed certificate is generated on the next generation firewall for connections to web servers with certificates signed by trusted certificate authorities. The newly generated certificate is imported to the client's browser certificate manager in order for the browser to recognize the next generation firewall as a certificate authority.
This is the browser certificate manager. And inside of it, you can see under authorities that there's a certificate with the name of 192.168.1.1. Now this is actually the certificate that we created in our next generation firewall. And by importing it, we can ensure that the browser recognizes it as a safe certificate. So now that we have our firewall configured, you can see we have to start a no decryption. So it checks whether the URL category is in financial services, government, or shopping, and if it is, it decides not to decrypt it. That way we don't accidentally disclose a user's personally identifiable information. Then we go through the decrypt user traffic, which catches anything that's not in those categories and decrypts it to make sure there's nothing nefarious within. And if we go to our device, we can look at our certificates, and you can see we have a trusted cert for trusted sites and untrusted cert for untrusted sites. And now, as you can see, if we go back to our anti-malware website and we try and reload it, you can see that it blocks. Our firewall has unencrypted this traffic, seeing that it's nefarious, and blocked it before letting us proceed.
The certificate in the next slide demonstrates that the traffic has been decrypted, inspected, and then re-encrypted as it initially wasn't trusted by the client browser. This can be determined by looking at the issuer name of 192.168.1.1, the name of the firewall on the client browser. After the decryption policy has taken effect, it was observed in the threat log that the traffic was a threat and had been decrypted. With this, we can verify that the decryption policies and trust certificates have been correctly configured to decrypt and re-encrypt the transport layer security sessions.
And here you can see that the certificate being used to access icar.org is the one that we created with our Palo Alto Next Generation Firewall. And this proves that this is the firewall inspecting and then re-encrypting the traffic before sending it to us. And in our Palo Alto firewall logs, you can see that there are many requests that are being ended, with decryption being set to yes, and the reason being set to threat. And this proves that our firewall is actually decrypting the traffic, detecting it's a threat, and then ending the communication.
We were also able to exclude government, shopping, and finance URLs from decryption as to avoid exposing personally identifiable information, or PII. With this, we were able to verify that the no decryption policy was in effect when viewing the certificate, since Texas page displays the issuer name coming from Amazon instead of 192.168.1.1. As demonstrated, we have successfully configured trust certificates and decryption policies to detect potential malware within encrypted traffic that would otherwise be able to reach client devices undetected. Testing confirmed that the decryption policies are functioning correctly, as indicated by the issuer name 192.168.1.1 on certificates from certain sites. This shows that the firewall is actively performing the appropriate inspections. In conclusion, the firewall's decryption, inspection, and re-encryption policies are effectively configured, enabling threat detection while maintaining privacy on sites with sensitive data.